of the super elevation process, but let's just go ahead and go through an example right now. Um, but before we do, I want to go ahead and bring your attention to something. What I want to do right here is draw the stages here of super elevation. Okay, and these lines here basically represent the ground. Okay, so this is the ground. All right, and I am going to really exaggerate the crown, okay, on the roadway. Okay, so here's the crown, and we're looking at cross-sectional views here. All right, so the first stage is to go from a normal crown to a length of tangent runout. All right, so if I'm going into the page, I'll probably have something looks like this. All right, and that's the tangent runout. And then I will be able to reach something called the continuous cross slope. All right, because hey, my cross slope is continuing through. And then finally, I reach the super elevation. All right, we should be okay with that now. But let's just take it from the continuous cross slope, because it may not always look exactly like that. Here's the reason why. When you have a continuous cross slope, when you finally get to that stage, you really have three options. Okay? Option 1, option 2, and option 3. Okay? Again, I'm just calling this my ground here, but different color just kind of differentiate that we're talking about two different things here. So once you reach the continuous cross slope, you have the option to rotate your section about outside edge, inside edge, or about the center. So you have option 1, option 2, and option 3. So let me go ahead and describe what this looks like here. Let's just say the pencil is basically the continuous cross slope. Okay, and now I need to super elevate it. Well, I can basically hold this at this pivot and super elevate it about the we call this the inside edge. Okay, so I can rotate about the inside edge and super elevate it that way. So option 2, we'll just call it rotate about the inside edge. All right. Well, what about option 1 here? Well, option 1, instead of holding my pivot there at the inside edge, I can pivot about the center and rotate it about the center. Now you see what happens when I rotate it about the center, right? This pretty much, this side of the edge is at a lower elevation than it was before. Okay. So option 1, rotate about center. All right, and I did that, I basically ended up, again, I was right here, hold the pivot here, rotate it about the center, fully super elevated, ended up something right there. All right. Option 2, if you remember, this is the continuous cross slope, rotated about the inside edge here, fully super elevated, kind of look like that. Okay. Well, option 3 is I can rotate about the outside edge, and again, I still want to make it super elevated, so when I rotate about the outside edge, again, I am at a lower elevation as far as the ground is concerned. Okay, so those are 3 options. Really, which one you choose depends on a number of things: how much cover you have, and what is near, or what type of utilities you might have on the ground. Just a number of different factors that can dictate which option that you use, and also which practice at the location that you'll be working. But that's just something just to know right there. Now, let's move on to an example. Here's a super elevation example. And in this example, we have 4 lanes, okay, and it's on the undivided road. The cross slope has been given to you. Of course, the cross slope, if you look at it in the cross-sectional view, is 2%, just to help out with drainage. Okay, of course, that's our crown there. All right, the design speed is equal to 45 miles per hour. That's been given as well. And the state mandates that on this road you need 6% super elevation. So that's been given. So these things are kind of held steady. Now, you've been asked to find the length required to super elevate from a normal crown. That's the normal crown. And determine where the transition begins and ends in reference to PC. So, if you look at this, remember I said PC can be right about here. Okay, so basically, where does this super elevation begin? Okay, well, to start to answer this question, we have to basically write a few things down. The first thing that I want to write down is my L sub T equation, which is equal to E, all right, normal crown, the percent of the normal crown, which was given as 2%, and also the super elevation, and all that's multiplied by your length of runoff. So your length of tangent runout is equal to this. Now your length of runoff is equal to your width of the road times the number of lanes that you'll be rotating times the super elevation divided by the relative gradient, and all of that's multiplied by your adjustment factor. Okay, so, well, how do we go about solving for this? Well, the first thing we have to do is figure out what our L sub r is. So I'll just continue on here. So my L sub r is equal to, well, I know it's 12-foot lanes, all right, and I know I have 4 of them, and I also know that the super elevation that the state mandated was 6. What I do not know right off the top is what my relative gradient should be, basically the rate at which the road is going to be super elevated, and the adjustment factor for the fact that I'm going to be rotating 4 lanes. Well, to figure out, let's just say the adjustment factor, I can just really apply the equation that was given to you earlier. 1 plus 0.5 times 4 minus 1, that 4 is the number of lanes that I'm rotating, all divided by 4. And then I end up getting a B sub W of equal to 0.625. And that is what I can put in here, 0.625. This can also be looked up in the table, except we don't have 4 lanes in that table that was given to you earlier. You see, if you remember, if you remember, this table only went up to 3.5, therefore I had to use this equation. That's what I did. Moving on to the relative gradient, I can see here that I should be using a maximum relative gradient in the percentage form, okay? Using this, you can basically divide 1 over 185 and end up getting this, but that's on the percentage form. So the relative gradient that I end up getting is for 45 miles per hour, because that was given to us earlier, all right, is going to be 0.54. So 0.54 is what I'm going to use. So now I have my L sub r. So my L sub r is equal to, when I multiply all of that out, I get 333.3 feet. Now because I have L sub r, I can figure out what L sub t is, which is simply the normal cross slope, which was given at 2, divided by the super elevation, which is also given now at 6. And remember, we're going to keep these in percent forms here, okay? Everything's in percent forms. That's in the percent form as well. Read that off of the table, the relative gradient. All right, now multiply that times your length of tangent run out. Okay, and when I do all of that, I end up getting length of tangent, I get the length of tangent run out of 111.1 here. Okay, so my length of tangent run off is 333.3, and my length of tangent run out is 111.1. Okay, well that's real significant. That's good information, because I can use this information now to determine the rest of what the problem asks. So I have my, say, my PC and my PT. Okay, and I know that they basically are connecting 2 tangents, and I wanted to determine, one of the things was, where should the transition begin? Okay, so basically, where should this transition from a normal crown begin? Well, one thing that I do have is my L sub r. Remember, I told you that L sub r straddles PC. Okay, so you can actually really split up an L sub r into 2 forms here. You can have L sub r where you have L1 and L2, okay, where L1 plus L2 equals L sub r. Alright, and L1, if you remember, I said I was going to use 0.7 here, so L1 is going to be equal to 33.3, which we already figured that out, feet, times 0.7, which is what we are going to use when we're determining the distance before PC. All right. And L sub 2 is going to equal 333.3 feet times 0.3. Okay. Well, this gives me 233.3 feet. So my L sub 1 is going to be equal to 233.3 feet. And my L sub 2 is basically 100 feet. So my L sub t is equal to 100 feet. Well, now that I know that L sub r represents that, and I know that my L sub t was already determined, and it was determined to be, if you look up here, 111.1. Then the total distance required, total length required to superelevate from a normal crown. Okay, let me just go ahead and push this up here. Total elevation required to superelevate from a normal crown is equal to L sub t plus L sub r. Alright, that is 111.1 plus 333.3. So the first answer that I'm going to get is 444.4, which we're going to round up to 445 feet. That takes care of the first one. So once I reach 445 feet into the curve from the very first location where we began to superelevate, I will now have a full superelevated road, and that will continue and basically just mirror what went on here. Okay. But the other question was determine where the transition begins and ends in reference to PC. Well, in reference to PC, the transition begins, let's just see, 233.3 plus 111.1 before point of curvature, and the road reaches full superelevation um, 100 feet after PC. So basically, this road has been taken from something like this, which is a normal crown, and at 111 feet looked like that, and then after 400 and about 45 feet, it was super elevated. Okay, so hopefully that kind of clears some things up going through that example problem. If there are any other questions, just let me know, and I'll be happy to answer them.